This example covers the last situation. In the last example, we did a partial fraction decomposition. That's very common in these problems. This is the other situation that's very common. So let's dive right in and take the Laplace transform of both sides here. We have s squared capital Y minus s times y of 0 minus y prime of 0 minus 2 times the Laplace transform of y prime is s times capital Y minus y of 0 plus 4 times capital Y, the Laplace transform of 4y, equals 0. The Laplace transform of 0 is 0. Now we can put in the values from the initial conditions, and we have s squared y minus 2s, y prime of 0 is 0, so minus 2s capital Y plus 4 plus 4y equals 0. Factoring the capital Y out of those terms, we have a capital Y times s squared minus 2s plus 4. When putting everything else on the other side, we have equals 2s minus 4. So we've taken the Laplace transform of both sides, we rearranged things. We can now say that capital Y, the Laplace transform of our solution, is 2s minus 4 over s squared minus 2s plus 4. Now this is where normally we would want to factor the denominator and then do a partial fraction decomposition. But this denominator doesn't factor. So we can't do partial fractions. This doesn't factor, which means no partial fractions. So what do we do instead? What we do instead is called completing the square. And we've probably done this before, and it's probably been a long time since you've done this. But we need to complete the square in the denominator. And the way we do that is we leave a little space after the linear term, after the s term. And what we're going to do is take the coefficient of the s, take this, divide by 2, and square it. So negative 2 divided by 2 is negative 1. Negative 1 squared is 1. So we add 1. Okay? And then since we've added 1, we don't want to change the function that we're working with. We also subtract 1. And then we still have the plus 4. And the point of that is that it allows us to write the denominator as a perfect square. That s squared minus 2s plus 1 is s minus 1 quantity squared. And then we're left over with the 4 and the minus 1, which is a 3. Now, that term is not perfect as far as the Laplace transform table goes, but it's close. It's close to things that look like things in the Laplace transform table. If we take a look at the Laplace transform table again, it's close to lines 17 and or 18, where we have s minus something squared plus k squared in the denominator. And so that's what we're going to be aiming at here. And we've done the completing the square. We took that term, divided by 2, squared it. That allows us to write this in a way that's closer to something in the table. So now we do want to keep working at this until it is actually something in the table. And so for that, what we need is we have the s minus 1 quantity squared. We're going to need an s minus 1 in the numerator. So let's go ahead and say that 2 times s minus 1. We're going to force it to fit what we want it to look like. So 2 times s minus 1. Now I can't, right now this equal sign is a liar. I haven't done what I need to do to make it equal. So really I have a 2s minus 2. I need to subtract another 2 here. And now when I look at it, 2s minus 2 minus 2, I do have the 2s minus 4. So that is equivalent, and it is written in the way that I want it to be written. So now I can write this as 2 times s minus 1 over s minus 1 squared plus 3 minus 2 times 1 over s minus 1 squared plus 3. And this isn't quite right. For this to fit into the table, I don't need a minus 1 here. I don't need a 1 in the numerator. I need a square root of 3 here, because I have to have a k squared. This is k squared, and I need a k in the numerator. So I need a square root of 3 up there. And we've already seen the trick for this. The only thing new in this example is the completing the square. Everything else is something that we've recently just seen. So I'm going to multiply and divide by the square root of 3. That doesn't change the value, but it changes how it looks, so that now it looks like something that's in the table. So this is all stuff that's out of our table now. We can now do the inverse Laplace transform, which will be the solution of our differential equation. So we have a 2, and this is an e to the t times a cosine of the square root of 3 times t, minus 2 over root 3 e to the t sine square root of 3 times t. That's the solution of our differential equation. We've seen solutions like this to differential equations back in chapter 4, and we could do this problem with techniques from chapter 4, but we've done it now with techniques from chapter 7 with the Laplace transform. So that's our completing the square technique. Together with partial fractions, those are things that are going to be encountered on pretty much every problem, every differential equation problem in this chapter. We're either going to complete the square or we're going to do a partial fraction decomposition. If we can't factor what we have, then we complete the square. If we can factor it, we do the partial fraction decomposition.